am recording, and I'm going to begin by hopefully sharing my tablet with you. So let's start with the browser. Let's start small. So hopefully everybody is seeing my Chrome browser, and I will show you our course. Okay, so here's where we are in the course. Again, week 9, you can see these due dates have changed. Okay, and you're gonna kind of you're gonna see down here. Okay, these due dates have all changed. Okay, so these used to be due on March 28th. We didn't have access that week, so everything's pushed out a week. So we have homework due on the 4th, and this is just a survey. My asking you how things are going, and this is especially important since we've had a week of downtime. Okay, let me know if you're concerned about anything, if I can help with anything. Now's a good time. We're kind of in the middle of the semester. All right, and you can see moving forward, all the dates are changed. Okay, going forward. So you don't need to worry that, oh my gosh, is this the real date? Is this a change? Everything's changed. Okay, now let me just show you backing up. Okay, here's week 8. Due March 14th, and I said everything from week 1 to week 8 was wide open. So you can see these dates are May 14th, which is our new end of the course. Okay, and if you go back through the course, anything that is a more assignment, like a homework, okay, that'll be May 14th. The discussion boards, okay, and the grade checks don't necessarily have changed dates on them. That's okay. You can respond to those late, okay? As long as I don't close the assignment, Canvas leaves it open. Okay, so if it's it's a Canvas assignment, like a discussion board or a grade check, those are fine. You can work on them late. And if it's a more homework, though, the date has to be opened. Otherwise, you can't use them. Okay, so going forward, all right, from week 9 on, okay, if you're late with any of those assignments, you're going to need late passes. Okay, and I've given everybody 2 extra late passes, okay, to kind of accommodate for this outage. All right, so you've got more resources, folks. Okay, my objective is to get everybody through the material in the course and understanding the material in the course, especially from here on to the end of the course. The material on probability and statistics will probably be the most useful math that you encounter in business. Okay, so even if you're not going to need it for another course, it might be relevant later on in your career. Okay, so I'm trying to make this as easy as possible. All right, so no late passes for the first half stuff if you've got any outstanding assignments you want to catch up with, but you will need them going forward. Okay, because these more dates are actually enforced by the system. Okay. So let me stop and ask, now that I've shared all that, anybody got questions? Questions on how the course will progress? Anybody? Questions on anything? Okay, so far so good, right? And again, if you've got questions going forward, feel free to give me a shout out and I will certainly work with you. Okay, remember, we have the capacity to do one-on-one meetings if that's something you feel you need. All right, that's what I'm here for. Okay, so give me a moment and I will connect my tablet and share these notes. I'm going to start with this topic, Bayes theorem. Actually, the notes are a little bit more expansive than just Bayes theorem. I'm going to start by talking about probability trees. You may or may not remember the last topic we talked about were conditional probabilities. Okay, probabilities when you have two non-independent events. That's where the outcome of the first event influences the probability of the second. For example, if you're being dealt cards out of a deck, your probability of getting an ace the first time is 4 out of 52, but your probability of getting an ace the second time is not the same because you've taken a card out of the deck and it's an ace. Okay, so that would be 3 out of 51. Remember, conditional probability. So we're going to talk about trying to handle these, keep track of these. Okay, when you've got a lot going on with a probability tree. And then we're going to expand that into this idea of Bayes' theorem. Normally, when you're doing conditional probability, you're interested in finding the probability of the second event, given that the first one happened, right? Like, what's the probability of getting that second ace, given that I got one the first time, okay? What Bayes' theorem lets you do, and it's sort of counterintuitive to most folks the first time they hear it, it kind of does the reverse. Let's say you know the probability of the second event, and you want to know what's the probability the first event occurred. Okay, so for example, when might you use this? Say you're looking at a defective part and it could have come from any one of three factories. And let's say you don't have a way to track where it came from. I realize with modern supply chains, that's kind of unlikely. But let's just say we have an old style operation here, okay? Given that you have a defective part, okay, what's the probability it came from factory A? That's a Bayes' theorem question. Here's the one, though, that grabs everybody's attention, okay? If I know I have a disease, then I have a pretty good idea, given the validity and reliability of a medical test, whether I'll test positive for the disease or not. This has been an issue with the COVID-19 pandemic. Some people were saying, I tested negative, but I'm pretty sure I had it, that kind of thing. Every medical test has what's called validity and reliability. In other words, does it measure what it's supposed to measure? And does it not, not give you a lot of false positives? Okay. Every test has these built-in errors because they're created by humans, right? So your question really isn't, given that I have a disease, will I test positive? It's the other way around. Given that I tested positive with this test, with this reliability and validity, what's the likelihood I actually have the disease I tested? Okay, that's a Bayes' theorem question. And it's a very timely one right now. Okay, so we'll talk about that as we move on. But that's just kind of an introduction as to where we're going. I kind of want to help reset you a little because I know it's been a while since you've looked at this stuff. Okay, so give me a second and I will get into my notes and share them with you. Oops. This always takes a while. Okay, and now let me share that content. So hopefully everybody is seeing probability trees and Bayes' rule. Okay, if you're not seeing that, shout out right now. Okay, I want to make sure everybody's seeing what I'm trying to project. Okay, so as usual, I'm not going to read the notes to you, but I'm kind of going to just explain as we go along. Okay, as always, shout out if you've got a question, just unmute yourself, type it in the chat. Okay, I have the chat open. Okay, so when we're dealing with multiple events like conditional probability type events where event one happens and that determines the change in the probability of the second event, it's pretty helpful to build what's called a probability tree. Now, even though they call it a tree, it doesn't grow up like a tree. It grows sideways or down, okay? And I'll show you how to build those. Okay, each branch will represent an outcome from a certain point. So every time you make a choice, you're going to wind up splitting the branch into at least two sub-branches. Okay, and then the probability attached to that branch is a conditional probability. Namely, what's the probability that that event happened, given that the ones further up the tree have already happened. Okay, so if you want to find the probability at the end of a path going through multiple branches of the tree, okay, you're just going to multiply along the branch, the probabilities along the branch. Okay, so to find the probability at the end of the branch, which is going to be that event A and event B happened. Remember, ANDed probabilities give you a multiply. you're going to just multiply the branch probabilities along the branch. Okay. If you're interested in going through multiple branches of the tree this way, okay, those are OR probabilities. In other words, I can get this outcome on this branch or on this branch. You're going to add those probabilities. Okay, so we'll see how that works with an example. Okay, so here's my probability tree example. Let's say I have a bag with 5 coins. 4 of the coins are fair, okay, which means the probability of a head or a tail is 1/2, okay? And 1 coin has a head on both sides. So what does that mean? That means the probability of tails is 0, and the probability of heads is 1. In other words, you can't possibly get a tail with that coin. With a fair coin, the probability of heads is 1/2, and the probability of tails is 1/2. Okay, now for those of you who are wondering, what do you mean a fair coin? Well, it's also called a biased coin, and it's usually done by weighting one side of the coin. Okay, so basically it's not symmetrically, it's heavy on one side. So when it lands, it always lands a certain way. Okay, so basically we have a biased coin, okay, and 4 fair coins. All right, so a coin is selected at random from the bag. Okay, here's event 1. Event 1. Okay, and then we're tossing it twice. So event 2 and event 3. All right, so we have 3 events here. The first one is picking a coin from the bag. Okay, so let me draw the tree for that. And again, I want to make sure I get this down far enough that I can fit the whole diagram. Okay. All right, so this is a choose coin, right? And let's say the first thing I'm doing is picking a coin out of the bag. Well, I have 2 choices. I can get a fair coin or I can get a biased coin. Okay, biased means not fair. Okay, well, if there are 5 coins in the bag, okay, what's the probability that I'll pick a fair coin? Okay, I'm asking you the question. What's the probability the coin I choose is fair? What's the probability the coin I choose? You've got a bag with 5 coins, 4 of them are fair, you're sticking your hand in and you're trying to pick one. What's the probability that the coin you choose is fair? Anybody have any thoughts? Well, here's a hint. The denominator of your probability fraction is a 5, right? Because there's 5 coins in the bag. How many ways can you get a fair coin? Anybody have thoughts on that? Yeah, 4 of them, right? If 4 of the 5 are fair, your probability of getting a fair coin is 4/5. Okay, there's only 1 biased coin in there. So you have a 1/5 chance of picking the biased or the not fair coin. Yes? Okay, so these are the probabilities on the first branch. They're not conditional yet because it's the first event. But think about it this way. You're going to toss these coins, okay? So your event 2 is tossing the coins, okay? And that definitely, the fact that you picked a fair or a biased coin definitely affects the probabilities of the toss. Okay, so let me do that one. Oops. I don't know why it did that. I didn't want to do that. Okay, here's toss 1. Heads. Oops. Sorry. All right, and here's toss one down here. All right, and we have to kind of figure out what are the probabilities on the branches here. Well, this is a fair coin coming down this pathway, right? So the probability of a heads is 1/2. Probability of a tails, 1/2. Okay, fair coin, no big deal. Remember, our biased coin has heads on both sides. Okay, what does that tell you? That tells you there's no way to get a tail. Okay, no way to get a tail. So on our first toss, this is our first toss. Okay, this was pick a coin. Okay, these are the event names down here, right? So there's no way to get a tail with a biased coin. So that probability is 0. And we are always going to get a head, so that probability is 1. Okay, so that's our first toss. And then remember, we also have a second toss. Okay, so here's the next event. Okay, and you can see how the number of sub-branches splits in 2 every time we make another choice. Okay, so here's our second toss, and I'll label them the same way: heads, tails, heads, tails, heads, tails. Okay, again, the fair coin is kind of boring. Okay, the probability is always going to be 1/2. Okay, and again, the biased coin, remember, there's no way to get tails with it. So any branch labeled tails is going to be a 0 probability. Okay, any branch labeled heads will be 1. Okay, so this is my completed probability tree. Okay, and what you want to notice here is if I look at this first series of branches, let me just highlight it on the tree for you. Okay, what that's telling you, what is the probability of picking a fair coin, right? And getting ahead on the first toss and getting ahead on the second toss. Okay, so think of it as probability of fair times probability of head first. Yeah, if I could spell. Given that it's fair, and the probability of heads second, given that it's fair. Okay, notice I'm not saying anything about probability of heads second, given that it was fair and given that you got a heads the first time, because the tosses are independent of each other. Okay, these are independent events. Okay, but picking the coin is not independent of the tosses because one of the coins is biased. Okay, so it's not flipping the coin that makes the probability change. It's the fact that you picked a biased or a fair coin. Everybody okay with that? Okay, so again, if I wanted to find the probability that this events occur, that I picked a fair coin and I got a head the first time and a head the second time, I would have to multiply these probabilities together. Okay, and there are a lot of problems on the next page that will kind of deal with that. And what's interesting is if you look, all of these branches will have probabilities associated with them like that. Okay, it turns out all of these branches up here in the fair part of the tree, okay, will all have similar probabilities because tails and heads have the same probability. Down here, not so much. you can see if you want the probability of picking a biased coin and getting two heads, well, you're guaranteed to get two heads if you flip the biased coin twice. So that probability is going to be 1/5. Okay? Anything else is going to give you a 0 because there are no tails possible with a biased coin. Okay? So any of the other branch probabilities in here will have a 0 in them. Okay, and so the probability of that branch ever happening is 0. Okay, everybody kind of understand that. Okay, well, again, I apologize because I'm going to have to go back and forth between the diagram and the questions, but I'll try to do it slowly so I don't make anybody nauseous, okay? But let's take a look at these questions. Use the probability tree to find the probability of obtaining two heads. Okay, so the first thing you've got to think of is how many ways can this happen? Well, we know it can happen with a fair coins, right? A fair coin. And we know it can also happen with a biased coin, right? Because the biased coin has two heads. So let's take a look at the tree. And I have one of those branches highlighted already. Okay, go down the fair coin branch. Here's the first head on the first toss, the second head on the second toss. And the other way it can happen is to go down the biased branch. Here's head on the first toss, head on the second toss. Now notice there are two separate branches. Okay, you want to think of everything on this branch as being anded together. Okay, so this is the probability of picking a fair coin and getting a head and getting another head. Okay, so these are all anded together. Hold on. Okay, and again, I'm finding the probability of this intersection using conditional probabilities, just multiplying down the branch. Here's another way to get a similar result. This is the probability of biased times the probability of head first, given biased, times the probability of head second, given biased. Right? And you can see those probabilities are 1/5 times 1 times 1. Okay, so everybody's seeing where I'm getting the probabilities. Okay, where I'm see where I'm getting them from. Okay. All right, everybody all right with that? Okay, so what I'm going to be copying back to the next page are these products of probabilities. So 4/5, 1/2, 1/2, 1/5, 1, 1. Okay, but these are two alternatives. So these are ORed together. So I can get the two heads either by going down the fair branch or by going down the biased branch. Okay, ORed probabilities are added. Okay, anded probabilities are multiplied. Okay, so let me go back here and put in those numbers. So the fair coin was 4/5 times 1/2 times 1/2. Okay, and the biased coin, I'll say or, which is a plus. The biased coin was 1/5 times 1 times 1. Okay, so again, all you need is a calculator to do this. And again, I can show you how to do that on the Web 2.0 calculator. Okay, to just multiply everything together. All right, so that would be 4/5 times 1/2 times 1/2 plus 1/5 times 1 times 1. Oops. Seems like I've managed to hang the calculator. Terrific. I am not sure what's happened here. Let me see if I can reload the page. Okay, try again. Huh. Okay, I'm not quite sure what's going on with this version here. This used to work just fine. I've tried reloading it, and it seems to be reloading okay. 4/5 times 1/2 times. It got stuck in the same place. Maybe it just doesn't like my syntax. Try it like this: 4/5 times 1/2. See, that's what I was afraid of. Okay, let's try this. That is so weird. It just didn't like the 4/5 in parentheses. I'm glad I tried it. 1/5 times 1 times 1. Okay, that looks right. 4/5 times 1/2 times 1/2 plus 1/5 times 1 times 1. According to order of operations, it's going to do the multiplies first. And I get 2/5 or 0.4. Okay, so my probability of this happening is 2/5. All right, so basically this is 2/5. So I have a 2/5 chance of getting 2 heads. All right, and again, this is probably not going to be the same as getting 2 tails because I've got the Bayes coin in the mix. Okay, so this was 2 heads. Here's 2 tails. Let me pick a different color to go down that tree. How about blue? Okay, so again, I can do this in 2 ways: with a fair coin or with a biased coin. And if you're already saying to yourself, no, you can't do this with a biased coin, you're absolutely right. That probability is going to be 0. But let's go back to the tree and see if we can figure out what branch to go down. Right, so I'm going to use blue for this one. So now I'm interested in 2 tails. So with a fair coin, that's going to be here, tails, tails. Okay, and if we look at that, okay, you can see that's going to be 4/5 times 1/2 times 1/2. Okay, actually following the branch probabilities on the tree. Okay, and if I go down the biased coin path, that's going to be bias, tails, tails, and you can see all the zeros that are there. So that's 1/5 times 0 times 0, which is 0, right? Because I'm multiplying by 0 here. Okay, everybody see where I got those from? Okay, you can, they look kind of greenish where I've highlighted it twice. Okay, but the blue paths are the paths for 2 tails. Okay, so let's go back to the problem. So with a fair coin, that's 4/5 times 1/2 times 1/2. 4 is a plus. The biased coin is 1/5 times 0 times 0. And I know that this second number is 0, right? Because I'm multiplying by 0. I really just have to worry about this first number. So if I go back to my calculator, maybe it will let me just like backspace over the second half of that problem, and I'll get the value of this. So let me try that. I'm going to click on this. Okay, just click up here. it'll put your formula back in the calculator, and then you can just backspace. Okay, and that's 0.2 or 1/5. Okay, everybody see how I got that answer? Now, you would expect with fair coins only, the probability of getting 2 heads or 2 tails would be the same, right? But remember, we don't have fair coins. We have 4 fair coins and 1 biased coin, which is why these probabilities aren't symmetric. Okay, you've got less of a chance of getting 2 tails because there's 1 coin in the mix that will never give you tails. Okay, that should make some logical sense. Okay, so everybody all right with these first 2 examples? Okay, could you just give me a shout out? Everybody okay with these? Yes or no? How are we doing? Making sense? How about the rest of you? Okay, got 14 people on. How are we doing, the rest of you? Anybody have questions? Okay. Okay. Well, let's see if we can find the probability of 1 head. And again, we've got a couple of different ways to do this. Okay, first of all, we can do it with a fair coin. Okay, and we can get head, tail, or we can get tail, head. Okay, so basically we've got 2 paths there. Okay, with a biased coin, and again, remember, some of these are not possible, but I'm writing down all of the possibilities that you would have to consider. Okay, so that would be head, tail. And again, people should be looking at that saying that can't happen. Okay, or tail, head. Okay, so again, you should be looking at this saying, that's not going to happen and that's not going to happen. Okay, so pretty much you can completely ignore getting 1 head and 1 tail from the biased coin. Okay, because you can never get a tail from it. Okay, but let's look at the possibilities. Now remember, each one of these is ORed together. Okay, so there's an OR here, there's an OR here, and there's an OR here. So you're going to be adding things together. You're going to be adding a bunch of things together here. Okay, but let's go down each of the branch probabilities so you can see where they come from. I'm going to get rid of what I have highlighted here already. Okay, so we can highlight the other ones. So if I want the fair coin, okay, and I'm interested in just 1 head, that would be fair, heads on the first, tails on the second, or fair, tails on the first, heads on the second. Okay, for the biased coin, go down here, heads on the first, tails on the second. Whoops, that can't happen. Or tails on the first, that can happen, heads on the second. Okay, so those are the paths I'm taking through the tree. As you can see, I've got 4 separate things and I'm adding them together. Okay, so going back over here, I'm going to put the probabilities in here. Okay, the probability of getting a fair coin is 4/5 times heads and tails, or 4/5 times tails times heads. I realize this may be confusing to you because the probability of heads and tails are the same. Okay, but don't worry about that. Just realize this is the probability of getting tail first. That's the probability of getting head second. Or if you try to do it with a biased coin, that's 1/5 to pick the biased coin. Probability of 1 for the head, 0 for the tail the second time. Or 1/5 times 0 times 1. Okay, and I'm leaving it to you to realize this product is a 0 and so is this one. So these two, you have 0 plus 0, that gives you 0. So you're only worried about these two, okay? And if you recall up here, we've already figured out that 4/5 times 1/2 times 1/2, that's 1/5, okay? So I have 1/5 here, 1/5 here. So this whole thing is 2/5. Okay. So hopefully everybody understands the generalities of how to do this. I'd like to move on to Bayes' rule because again, I don't want us to run out of time, but everybody understand the general idea of a probability tree. Okay, understand the general idea? You and your way down a branch to get to the probability at the end. Okay, so it's this probability and this one and this one. You OR the probabilities in the different branches together with adding. Okay, so everybody good with that? I'm going to skip this last example so we can move on. Okay, and again, if you're having issues, you can always message me privately to let me know. Okay, and I can go over stuff. Okay. Well, let's move on to Bayes' rule then. Now, suppose you knew the outcomes of the coin tosses, but you wanted to know the probability that the coin you were tossing was fair. Okay, so let's say I didn't tell you one of the coins was biased and I let you do the two tosses and you got these results. Would you be able to tell you were using a biased coin? Okay, so let's think more about how you would calculate the probability of using a fair coin, knowing the outcomes of the coin tosses. Okay, so let's say the first coin toss resulted in tails. Okay, find the probability that the coin used was fair. So you want to find the probability that the coin is fair, given that the first toss is tails. Okay, so if you remember the conditional probability formula, this is the probability that the coin is fair and the first toss is tails, divided by the probability that the first toss is tails. Okay, so basically, I guess I should keep my writing the same. The first toss tails. Okay, so that's the way you do conditional probability. You and the two events together in the numerator. So fair and first toss is tails. Bottom is the first event. Remember, the first event is what comes after given that. Okay, so let's take that stuff, okay, from the tree. Okay, the probability that it's fair is 4/5, and means multiply. The first toss is tails. That probability is 1/2. Okay, and then you have all the different ways to get the first toss to be tails. Okay, so this is okay, all the ways to get tails on the first toss. notice this isn't saying anything about whether the coin is fair or biased. Okay, so this event down in the bottom is going to have a plus sign in it. Fair or biased. Okay, so how do I get tails on the first toss? Well, 4/5 times 1/2, right? That's getting a toss on the first, getting a heads on the first toss, given that the coin is fair, or getting a heads on the first toss, given that the coin is biased, is going to be 1/5. I'm getting tails, rather. Tails are 0. Okay. So I have in my denominator all the ways to get tails on the first toss. Okay. So this is the product of the branch probabilities down to the event I'm interested in. And this is all the ways to make that first event happen. Namely, the first toss is tails. Okay. Now you'll notice this part of the denominator will cancel out. So your numerator and denominator, okay, is basically the same. That means your probability is going to be 1, which means it's absolutely certain. Think about that for a minute, okay? You're asking, given that I tossed a tail, what's the probability the coin is fair? Well, it has to be a fair coin because the biased coin doesn't have tails on it. Okay, so you're absolutely certain to be using a fair coin if you get any tails, right? So that's what this certain means. And again, what would you think would be the probability here? Okay, if you toss tails on the first toss, what's the probability the coin isn't fair? Think about that. Think about it from a logic point of view. If you toss a tails on the first toss, what's the probability your coin isn't fair? Anybody have any thoughts on it? Does the biased coin have tails on it? Can you toss tails with the biased coin? Anybody have thoughts? No. Okay. You can't toss tails with it. So you would expect the probability of tossing a tail with a biased coin would be 0. Let's figure it out. Okay, so again, that's the probability that it's biased. And first toss is tails. And the denominator is the probability that the first toss is tails, no matter how I get that to happen. Okay, so I already have the denominator, right? That's the same denominator as first time, 4/5 times 1/2. That's with the fair coin. Or 1/5 times 0. That's with the biased coin. This is all the ways to toss tails first. Okay, and then the probability of having a biased coin, that's 1/5, and tossing tails with it first, that's 0. So if you take a look at this fraction, you've got a 0 in the top, right? And this is going to give you like a 2/5. 4/5 times 1/2. Half of 4/5 is 2/5. This goes away. So this becomes 0 over 2/5, which is 0. It doesn't matter what the denominator is as long as it's not 0. Okay? So there's no chance of this happening. Okay, so this is certain. This was no way. Okay? Everybody understand that example? Everybody understand problem 1? Yes? No? Okay. Again, I appreciate the feedback that some of you are giving me privately. That's very helpful. Okay. Let's take a look at one more example like this. Again, I reserve the right to leave out examples if it seems like people are okay with it. I will upload my notes with all the examples completed so you can refer to those. But let's take a look at this. If the first coin resulted in a heads, now see, this one's a little more complicated because I can get heads out of the biased coin. Okay, so this is a little bit different. Okay, so find the probability that the coin was fair or biased. Okay, I'm going to move this onto this page so we can work all at once. Okay, I know this is on the next page, but there you go. Okay, so this means find the probability that the coin is fair, given that the first toss is heads. Again, let's figure it out. This is the probability that the coin is fair and the first toss is heads. And this is going to be all the ways to get the first toss heads. Okay, so now I have some more alternatives, okay? Your numerator is the probability of a fair coin and getting heads the first time. That's 1/2. Okay, so I'd expect that. Okay. Now I have to think of the ways to do this with a fair coin and a biased coin. Well, I just figured out the fair. Okay, that's what's in the numerator. And that's an artifact of Bayes types problems is whatever is in the numerator is what starts the denominator. Okay, so basically I'm going to have 4/5 times 1/2. I kind of reversed it here, but you can see the numerator is in the denominator. It's one of the alternatives. Okay, so that's the way to get it with a fair coin. But I can also get heads with a biased coin. Okay, that probability is 1/5. Okay, and the probability of getting a heads is 1. I'm guaranteed to get a head with the biased coin because that's all it has. Okay, so if you figure this out, this is going to give you 2/5 on top and 3/5 on the bottom. Okay, and again, I'm just using a calculator to add the fractions. Okay, if you're doing this on a TI, okay, you can either use the fraction template, okay, or you can just add your fractions together, add and multiply, and then use math frac at the end. Okay, so however you want to do it. All right, or you can do it on the Web 2.0 calculator. Okay, I'm going to bring up the TI briefly and share it with you. Okay, you should all see my TI. All right, and if I want to do this, I can type it just the way it looks. Okay, I'm going to use the fraction template, which is alpha y equals, yeah, clear, alpha y equals numerator denominator. Okay, and I can do it again in the numerator. So I can say alpha y equals, but make sure you're in the numerator when you do this. Okay, so I have 4/5 times, and then alpha y equals 1/2. Okay, so that looks exactly like what I have here. And then I'm going to do the same thing here, alpha y equals, just make sure you're where you expect to be when you open the template. Okay, so 4/5, arrow over, times alpha y equals 1/2, arrow out, then plus alpha y equals, select it, 1/5, and then times 1. Okay, the beauty of this is it should give me a fraction. Okay, so you can see 2/3. Okay, if you use the fraction template, you don't need math frac, it'll do it for you. Okay, now if you look at this complex fraction I have here, you can just cancel out the 2 5s as a denominator and you'll get 2/3. You can also multiply 2/5 by the reciprocal of 3/5, which is 5/3. Either way, you're going to get 2/3. Okay, everybody see how that one works? If I try it with a biased coin, that's going to be the probability that I have a biased coin, given that the first toss was heads. Okay, so again, that's the probability that it's biased, and first toss heads divided by the probability that the first toss was heads. And again, remember, this is all the ways. Okay, so the probability that the first toss is heads is the same denominator as I used here. Okay, what you want to remember is you've got fair and biased. Okay, so I've got 4/5 times 1/2 plus 1/5 times 1, same denominator. And I'm interested in biased and the first toss being heads. Well, that's the same as 1/5 times 1. Everybody good with that one? Okay, so that's going to give me 1/5 over 3/5, or 1/3. Okay, so basically, they're saying if your first toss was heads, you've got a better chance of having a fair coin than a biased coin. Well, yes, that makes sense because there are more fair coins in the bag. Okay, but again, you don't have a symmetric situation because this coin, the fact that it's biased, is changing the probability of the subsequent events. Okay, but what I want you to see, an example in problem 1 and problem 2, is the structure of the fraction I'm building. Okay, you've got the two events that you're interested in anded on the top, and then the bottom is all of the ways, all of the branches through that probability tree that give you, say, first toss heads. Okay, so you're adding all the ways to get there, fair or biased. Okay, so see the structure of the fraction. That's going to be important when we talk about Bayes. Okay, everybody see the structure? It's not about the numbers that are in there so much as, do you see how I built it? Okay. All righty. Okay, so what we're going to do, I'm going to pass this over, and I'm going to basically talk about Bayes' theorem. Okay, Bayes' theorem is when you know the outcome of your second event and you're trying to determine the probability of what happened first. Okay, so basically, let me show you the product rule. which again, we did in section 7.3. Okay, so the product of A and B is the product of A times the product of B given A, or it's the product of B times the probability of A given B. Okay, and the difference between these is which comes first. Okay, A first, B first. Okay, with whatever events in order. If I just have the two events ANDed together, A and B, you can't tell which one was first or second. So you've got two choices. Okay, remember, with conditional probabilities, your probability of your first event isn't changed. It's just that probability. It's the conditional probability that's different. Okay, so this is the probability of your second event B, given that A already happened. This is your probability of your second event A, given that B already happened. Okay, so kind of complete that there for you. Okay, everybody remember the product rule? Okay, remember the product rule. But again, I don't mean remember it in the sense that you recall it. I mean, do you remember, do you recognize it, that you saw it before? Okay. There you go. So that's the conditional probability product rule. Okay. Remember, if there is no conditional probability, it's just probability of A times probability of B. Okay. But if the first event affects the probability of the second, you're going to need these conditional probabilities. Okay. All right. So one way that we can write the probability of A and B is probability of, I'm just copying. Okay, so this is A first. And I can also do the probability of B times the probability of A given B. And this is where B is the first event. Okay, so I'm just copying that from the bottom up here. All right, here's the conditional probability formula. The probability of A given B is the probability of A and B over the probability of B. Here, B is the first event, right? A given that B already occurred. That means B was first, A is second. So your first event goes down here. Okay, which of the formulas you wrote in question 1 doesn't have the probability of A given B? Well, that would be the first one. That's B given A. Okay, so that would be this one. Okay. And then rewrite the formula. We're deriving the Bayes rule formula. Okay, so here's the Bayes rule formula. Okay. Okay, so there's the path to A and B. And here are all the ways B can occur. All right, everybody good to that? Good with that? Okay. So here's our Bayes rule formula. Okay, now what you want to notice, and this is where people tend to get tripped up. See this and that, okay? They mean different things, okay? But it gives you a way to go backwards, this is that backwards, okay? So here, okay, we're saying, well, given that you know the second event happened, what's the probability of the first? Okay, so basically this gives you a way to go backwards, the reverse probability, okay? Finding the probability of that first event is easy, but sometimes going down the path, this is multiple paths in the tree. Okay, just like we did with the fair and biased coins. Okay, so rather than talk about it more, let's actually show you some examples. Okay. All right. Use Bayes' formula to calculate the probability. Oh, and this is misspelled. It's actually, the guy's name was Bayes, okay, with the S on it, okay. He was actually, I think, a 19th century clergyman who happened to have an interest in mathematics and came up with this. At that time, probability was pretty much used almost exclusively for two things: gambling and insurance. Okay, and I believe he was interested in the insurance applications of it. But anyway, we're going to try to use the formula to figure out the probability that the coin used was fair, given that the toss was heads, first toss. Okay, so what we're trying to find is the probability of a fair coin, given that the first toss was heads. Okay, then let's do the rest of the formula with words. Okay, so the rest of the formula is the probability that it's fair coin. Okay, again, let's call this the probability of A given B. Again, let me write this in a different color so it stands out. So fair coin is A, B is first tosses heads. Okay, so I want the probability that it's a fair coin given the first toss was heads. So here's the probability of A times the probability the first toss was heads, given that the coin is fair. Okay, so that means this is the probability of B given A. Okay. And then in the denominator, I want the probability first toss heads. Okay, and this is the probability of B. Okay, so there, the red stuff is the Bayes rule formula, and the black writing is it interpreted in the context of the problem. Okay, and again, you can see I have A given B. Here is what I'm trying to find. There's an equal sign here, equals, and it equals this right-hand side over here. Okay, and here's the B given A. This is the stuff I can figure out from my probability tree. Okay, the probability that the first toss is heads, given that it's a fair coin, that's 1/2. Okay, so let's do it with numbers. Okay, so the probability that I have a fair coin, that's 4/5. Okay, so here's A. And then the probability of B given A, that's the probability that I get a first toss of heads given that the coin was fair. That's 1/2. Okay, and then this is all the ways to toss heads. Okay, so this would be, whoops. There's two ways to do this. Okay, there's the probability that I have a fair coin and that I get heads given that it was a fair coin, or there's the probability that it's not a fair coin and that I get heads given that it's not a fair coin. Okay, so this is fair or biased. Notice I wrote the probabilities, the conditional probabilities with a complement, okay? This accent mark can also be written as a C, like this, okay? However, complement is written in a whole bunch of different ways, and it just matters how you learned to write it the first time. So I learned to write it with the accent mark, so that means a complement. Some of them also do it with a bar over the A. Again, different people came up with different notation. Okay, so if I plug in these numbers, this is 4/5 times 1/2. And again, notice the first thing in the denominator matches the numerator here. Okay, or it's biased, and I get heads the first time, given that it's biased. Okay, and we already figured this out. This is 2/5 over 3/5, or 2/3. Okay, but here we did it actually explicitly using the Bayes formula, rather than having to build a probability tree. So you might be saying, well, wait, I mean, we did this already, so why are you showing me a different way? Because if things get complicated, probability trees are not reasonable, okay? They get unwieldy in a hurry, okay? So this Bayes theorem kind of gives you a compact way to deal with conditional probabilities, okay? So again, let me, I see we're getting close towards the end, okay? I want to make sure that we see problem 2, okay? Again, when I upload my notes, I'll upload all of the stuff in the notes, but I want to not overwhelm you. Okay, so again, here's the rewrite of Bayes. Product of branch probabilities on a path through A leading to B. So this gives you A and B. And the denominator is the sum of branch products on all paths that lead to B. Okay, that's how you do this. Okay, it is really, really helpful if you think of Bayes' formula in this way. Okay, otherwise it's just a jumble of letters and you're going to get lost. Every Bayes problem comes to you in words. Okay, so it's important that you understand what it is you're finding the probability of. So let's do an example like that. Okay. And again, I apologize for the timeliness of this. It has been in these notes for a while. Okay, so let me show you this. A test for diagnosing a recently discovered serious disease is successful in detecting the disease in 95% of all those who have it. Okay, but incorrectly diagnoses 4% of healthy people. Okay, so essentially, this is called a false positive. Namely, your test is saying you're ill when you're not. Okay, every single medical test has these limitations. Okay, scientists know that 2% of the population have the serious disease and 98% is healthy. Okay, so maybe this is some rare disease they've just discovered. Let's draw a probability tree that represents the situation. Okay, so we're going to start out by saying, well, you either are ill or you're healthy. So this is going to be disease. That is 0.02, so that's 2% of the population. Okay, healthy. 0.98. Okay, so that's the first thing we know. We also know that this test finds 95% of all the people who are ill. So here's test positive, test negative. This is 0.95. Okay. We also know down here of all of the healthy people, some of them are going to test positive in error, and some of them are going to test negative, which should be the bulk of them. They tell us that 4% of healthy people will test positive. So this is called a false positive. Okay? This is called a true positive. Okay? Namely, you have the disease and you test positive for it. Okay? False positives are upsetting. Okay? If it's you getting this medical test, it's very, very nerve-wracking to be told you had a positive result and then to later find out, oh no, you're fine. Okay? Standard situation, a woman goes for a mammogram, the radiologist sees something suspicious, wants to do more tests. Very nerve-wracking, but it's great when you get the call back saying, no, it looks fine, you're fine. Okay? The worst case is this one right here, okay, where you have a disease, but the test doesn't catch it. Okay, this is called a false negative. Okay, and false negatives in medical tests can be lethal. Okay, namely, you're not going to do anything about it because you think you're fine. Okay, so that's really the case that you kind of want to avoid. All right. So let's think about how we fill in the rest of the tree. Down here, we have a true negative, namely, we've got somebody who isn't ill and tests negative for the disease. That's great. Okay, so let's take a look at what else. This is all of the information given in the problem. Okay, so, okay, if 95% of the people with the disease test positive, then that must mean the remaining 5% of the people with the disease test negative. Okay, this is of the people who have the disease. Okay, likewise, if 4% of the healthy people get a false positive result, that must mean 96% of them test negative like they're supposed to. Okay, so notice I had to fill in these numbers. I had to figure those out. And how did I do it? I just took 1 minus what I was given. Okay, now this isn't that unwieldy as a tree, but usually this data, this type of data is presented in a table. Let me show you how to do this in a table. Okay, so disease test table. Okay, let's do it like this. Make it a little more symmetric. Okay, so here we're going to have a column called disease, healthy, total. Okay, and over here we're going to have test positive, test negative, and total. Okay. All right, so I basically need to know the product of the branch probabilities to get to I have the disease and I test positive. Well, let's go down that branch. The disease is 0.02 and I test positive. That's 0.02 times 0.95. Product of those branch probabilities. Okay, I have the disease and I test negative. That's this way. 0.95 times 0.05. Okay, I'm healthy and I test positive. That's my false positive case, 0.98 times 0.04. I'm healthy, but I test negative, which is what I'd expect, 0.98 times 0.96. Okay, then you take a calculator and you figure out these products, keeping as many decimal places as you can. This gives me 0.019. This gives me 0.0392. This gives me 0.02, which I'd expect, okay? Because, wait, I'm sorry, wrong thing. 0.001. And this gives me 0.9408. You can see the bulk of the people, 94%, are healthy and test negative, which is great. That's what we expect. Okay. Now what you want to do is you want to add this stuff up. Okay, let's add up the columns. Okay, so I'm adding the 0.019 and the 0.001. I think you can see that gives me 0.02, which is the 2% of the population known to have the disease. Okay, also, if you add up these numbers.
Ms. Smith,
Yes,
I have a question
go ahead.
where it says disease and test negative, you put 0.95 times 0.05, isn't it 0.02 times 0.05?
Yeah, my bad. Sorry. Thank you. Thank you for catching that. Thank you. You're right.
Yep, you're welcome.
Okay, so yeah, the disease column has the 0.02 and the healthy column is 0.98. Right. So there should be a certain symmetry when you do this. Thank you for pointing that out, Daisy. Okay, so if you multiply 0.02 times 0.05, you get 0.001, right? These two multiplied together, okay, give you 0.019. If you add the two numbers that are highlighted in yellow, you get the 2% of the population known to be ill, okay? These, if you add the blue highlighted numbers, you should get the 0.98% of the population known to be healthy. Okay, likewise, you can add across the rows like this. Okay, so if you add across the rows, and there's really no reason to do this, let me just point it out to you. Okay, I'm trying to do this so you can see. Okay, this is telling you what percent of the people are going to test positive and what percent are going to test negative, regardless of whether they're ill or healthy. Okay. Now, what's important is this lower column. These two numbers need to add to 1, and these two numbers need to add to 1. Okay. So that last column, corner cell in your table is a check that your numbers are right. Okay. If this total column adds to 1 and this total row adds to 1, you've probably done the table correctly. Okay. Doing it in the table also gives me the ability to consolidate my information. Okay, so let's take a look at the question for part B. You have been tested positive for the disease. What is the probability that you actually have the disease? So what you want to know is the probability that I have the disease, given that I tested positive. Okay, so in words, that's the probability of having the disease and testing positive. Okay. And that down here is going to be all the ways to test positive. Okay, so that's the Bayes theorem formula in words. Okay. So if you think about it, looking at your table up here, the probability of testing positive and having the disease is this 0.019. Okay, I'm going to write it out the way I did. 0.02 times 0.95. Okay, so that's the product of the branch probabilities that go from disease all the way to testing positive. Everybody see that? That goes up here. Now you need to find all the ways you can test positive. Well, you can test positive if you've got the disease, but unfortunately, you can also test positive if you don't have the disease. That's the false positive case. Okay, so let's take a look at our table and try to do Bayes at the same time. I wish I had written just a little smaller. Okay, so one way to test positive is to have the disease and test positive. The other way to test positive is over here. Okay, it's to have to not have the disease and test positive, the false positive case, this one. So that's 0.98 times 0.04. Okay, everybody see the way I filled in my Bayes fraction? Okay, take a minute and look at the table. Okay, and see how I pulled the numbers into the Bayes fraction. So this is testing positive and having the disease. This is testing positive and being healthy. Okay, the rest of it is just arithmetic on a calculator. Okay, if I actually put these numbers into my calculator, okay, and get a numerator and denominator and divide, I'm going to get a number that's about 0.3265. Okay, so what does that tell you? If you test positive, you have about a 33% chance of having the disease. Okay, now this is usually an eye opener to people. They say, wait, what? So I got a test and it said it was positive, but there's really only a 33% chance I have it. Yes, that's why you shouldn't freak out when you have medical tests. One of the things you should ask the doctor is, what's the true positive rate on this? What's the true negative rate on this? Okay. Part of the reason why this probability is so low is because not many people in the population have the disease. Okay. Neither of these false positive or false negative rates are terribly high. Okay. But see the effect they have on this reverse probability. Okay. So most people, when they first see this, it's a very counterintuitive result. They don't really, like, why is it so low? And again, part of it is because it's a rare disease. Not many people have it. And part of it is every test has these false negatives and false positives. Okay, and you have to account for that when you interpret the results, which is usually why your doctor will say, look, we got a positive result, let's do some more tests. Okay, it's not that they're trying to, milk you or anything. It's that they have to account for this effect. Okay, so let me stop and ask any questions on using Bayes rule. Any questions on this, folks? Okay, take some time and actually pay attention to the words in the problem. Make sure you're figuring it out. And I recommend you try to build a table. I think it's easier in a table than a tree. Anybody questions on this? Okay, I'm going to stop sharing. Okay, how about anybody questions on anything? Anybody have general questions about anything?